My name is Pawin Teshayotin from Darun Sikalai School, Science School. I will be the reporter.
My name is Watanyu Fusang. I'm an opponent.
My name is Chanakanwa. I'm as a reviewer.
Good afternoon, everybody. My name is Pawin Teshayotin. Today, I'm going to present about colored plastic. The problem states that in bright light, a transparent plastic object such as a blank CD case can sometimes shine in various colors. Study and explain the phenomenon ascertain if one also sees the colors when various light sources are used. First, let's look at the underlined words. Transparent plastic object. I defined it, I think I'll use a blank CD case as a transparent plastic object. Sometimes shine. This means that not in every condition does it shine. There are only specific conditions that need to be met for it to shine. The problem wants us to study and explain the phenomenon and also make sure if we use various light sources, what will happen. Basic observation 1, unpolarized light source. We use the lamp and the light will be reflected to the camera from these angles. From the first view, the 80-degree angle, we cannot see any colors. Then with the 55 degrees, we can start seeing colors, but it is very hard to see. So the reflection angle matters. Next, we'll use a polarized source, which is an LCD screen. On the top is we use the camera without a circular polarizer as a filter. You can see that there's a very faded light in the CD in the 3 pictures. And with the polarization filter, the fringes are much clearer. So it's easier to see with a polarized source. That means polarization does matter. And the polarization helps enhance the effect. Next, we'll look at the theories. First is electromagnetic wave, which we will be only interested in the electric field, which the electric field are we can see them as 2 components, which is the X component and the Y component. This is the equation of the oscillatory of the electric field, which this thing over here is called polarization. It is the direction of the oscillatory of the electric field. Polarization is the direction of the oscillatory, as said before. And there are special cases such as linear polarization. If the phase difference is 0, pi, 2 pi, 3 pi, or 4 pi, it will be a linear polarization. And if it's a circular polarization, it will have to have the amplitudes of the X and Y equal, and the phase difference will be pi minus 2, 3 pi minus 2, something like that. And other cases are called elliptical polarization. Birefringence is a material that has more than 1 refractive indexes, which causes a phase retardance between the X and Y component. Overview. I've divided into 4 experiments. First is the polarization axis. The colors does the CD cause excitation? And the 4th is rotating the CD case. And then we'll go to the conclusions. The experimental set. We have a LCD as a polarized light source, the CD case as a sample, and the polarizer as an analyzer. and then the camera to record the picture. Experiment 1, polarization axis. Hypothesis. Polarization axis affects the fringe pattern. This is the results. You can see from different angles of the analyzer, which causes a difference in polarization. There are different patterns. See, the dark spots are not the same position. Comparing with the hypothesis, yes, the polarization axis does affect the fringe pattern. This is because fringes are caused from areas that make the transmitted light polarization cross with the analyzer. Possibilities of this phenomenon. If the light passes through the CD case and has a linear polarization, it could mean that the dark areas in the picture have the same polarization axis as the LCD. Other areas could be cause of circular or elliptical polarization. Next is colors, if different colors give fringe patterns. These are the results. You can see from different LCD screen colors, they give different patterns. And when we merge the red, green, blue pictures together, we get something like this, which we compare with the original white. It is quite similar. This is the graph of the intensity of the red component. And this is the green compared with the original white and merged one. And this is the blue one, the blue component. Yes, different colors do give different patterns, but when merged components of colors together, it will give a pattern similar as the resulting colors pattern, such as red plus green plus blue equals white. Excitation. The CD case does not cause excitation, is what I think. Then we'll use a spectroscopy to measure the wavelength of the light coming from the LCD screen and the compare results with the CD case between the spectroscopy and the LCD screen and without the CD case. From this graph is the results from the spectroscopy, which there is no excitation because there are not any new peaks appearing. So the CD case does not cause excitation. From the resulting graph from the previous slide, the only difference between the with and without the CD case is the amplitude. So there is no excitation. And the last experiment is rotating the CD case, which the LCD and the analyzer is set to cross-polarized. So rotating the CD case causes the pattern to differ. I think the patterns will change when rotating the CD case. These are the results. When we compare each angle together, it is the same, but the reason there are slight differences is because these angles are approximately, not exactly. So rotating the sample does change the fringe pattern. As seen in the results from the previous slide, as the CD case is rotated by 45 degrees, the patterns change. But if we compare two angles that have a difference of 90 degrees, 180 degrees, 270, and so on, they will have the same pattern. Conclusion. The polarization axis has an effect on the fringe because it determines the ability to pass through the analyzer, which rotating the transparent plastic object will cause a difference in the axes, resulting to a changed fringe pattern. Then the color changing will affect the pattern as well. But however, there is no excitation caused from this plastic object. Thank you.
Okay. The first question, could you please go to the slide that you have 3 types of polarization? Yes. So I'm wondering why it has to be this angle to like why it has to be pi over 2 to be a circular polarization. Can you show me?
Yes. Because from this picture, you can say it goes something like this. And this is the y component, and this is the x component. Something like that.
Uh-huh.
So this, as two vectors are merged together, it gives this, something like that. So if it's a circular polarization, means it will rotate because there are different amplitudes. With the two components are different, the direction, something like this. If as the x increases, so if the y is something like this at the top, and the x must be 0,
Uh-huh.
because the full amplitude is something like this. This is the amplitude of the electromagnetic wave.
Seems you don't get my question. Yeah, why? So you say it has to be pi over 2 to be a circular polarization?
Yes.
Why?
Because the shift of phases.
How? Shift? What is how is shift and is come to be circular polarization?
Okay, assuming that these two are different, these two are the same. The difference is only this and this. It is the phase, a starting phase. If the phase is 0, the phase difference is 0. So as y increases, the x increases as well. So the
So,
pattern will be like something like this, but it will become smaller, 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 and go back again.
So you're saying compared to a sine wave graph?
Yes.
Okay. Next question. I'm wondering why the different angle give the different pattern of fringe.
Because when we rotate the analyzer, the light that can pass through the analyzer is changed because the angle of the analyzer is changed. So an analyzer is like the light that has the direction in the same direction as the polarizer.
Make the unpolarized light to be a polarized light.
Yes.
And so you say if we look at a plastic in different angle, so you say that we will see the different fringe.
Yes.
And is also for color. Different angle, different color.
Different angle, different color. Yes, because as a single color changes, the dark areas, when there are light composed, like said, white light is composed from red, green, and blue, like this one. If the areas like this are black, and the pattern of the green light is not, this is not black, but it's somehow green. The green will replace this black one, and the intersections of the areas will merge together and causing a new color.
So is it depends on refractive index?
Yes, because it depends on the refractive index of this material.
So
The birefringence material, the refractive index is determined when compared to the polarization axis of the material.
okay, I saw you use two different light sources, that original white light and merged light from RGB.
Yes.
So is actually white light, but what's the difference of these two sources?
The difference is this one I use the LCD screen as white and capture the pattern image. And this one I use the LCD red and capture the image. This as the red, is same as the red, and the blue as the green and the red. So these are different pictures taken, but this is a single picture taken.
So why do you have to use
Red, green,
red?
and blue.
Yes.
Because
Instead of use just one the original white light.
Because right now we're comparing if different colors give different patterns. So we have to use different colors, not only just white. Because
so-
if you use only white, this experiment
And-
won't be valid.
Do you think you use three, including white as one color?
Yes.
Four colors, and
Actually,
is that enough for make the conclusion for the whole wave? Every value of wavelength.
I think it is enough because the red, green, and blue are the master colors of the light displaying system. So we can just merge these two together in the different ratios and and we can get another color.
So have you tried to put it together? So like put red and green together and see
Yes,
other color.
it results in the yellow color, which I didn't put in the slide, but I have the photo of it.
In in one of the experiments, you use the CD case.
Yes.
I wonder what like what's the not shape? What's the CD case you use? What is this shape like? What's the shape? Not shape. You use a CD case, just one sheet of plastic or
Yes.
a whole case.
Just one sheet. Or
It like the CD case. You
only one
did
side.
experiment only one side.
These are two sides. I used only one. This is not involved. Only one.
And this is just refractive
This is in transmission mode.
transmission.
Or furthermore of the reflection mode will be
So
carried on in the further experiments.
you didn't mention about the reflection polarization.
not
It's just
yet.
refract. Okay, thank you.
สรุปด้วย
Time for me to summarize. Okay, for first question about each type of polarization. He told that to to be a different type of polarization, just linear, elliptical, or
Elliptical.
like that. It depends on the angle, or it is called phase of the two light source, the different phase. And the different angle and different color give the different pattern of fringe that occur on the CD case, plastic sheet. Thank you.
Okay. Okay, from the discussion of reporter and reviewer, the good things of the reporter is he define for his definition is very clear. The pictures is very beautiful and easy to see the phenomenon. And he wrote a line that makes when he analyzed the data is that makes it easy. So, but in presentation he has a lot of equation, but he not explain about the equation. And about an experiment that he vary angle, he didn't tell us about what axis that is the reference axis, that I confuse it just a little bit. And in his presentation is not explain about the phenomenon, but how the wavelength have an effect with the phenomenon, why it be like this, but he didn't explain. But for the opponents, I agree with him too. He asked him to explain the equation and ask for explanation of the phenomenon, that how the wavelength or how the theta has the effects on the phenomenon. But he just a little bit that he don't ask about the relationship. No, but he didn't ask that where is the energy. But for the reporter, he told that when the light through from the polarizer, there just two axes, the light just passed just two axes, that he told us that the bottle the CD case is not excited. So the opponent don't ask him where's the energy. So, thank you.
Excitation. What I mean by excitation is when electrons absorb an amount of energy, it goes to an excited state, which is become unstable. Then it releases that energy and it goes back to its ground state, which the energy released is light that will cause new peaks in the wavelength graph.
So, what is the source of the excitation?
Source of the
Who causes?
The molecules of the CD, the molecules of the object.
The CD cause the excitation?
I said it doesn't cause excitation.
Right.
If it cause, it will.
No. Do you know about the cause and effect? the CD will cause the excitation or something else cause the excitation in the CD?
I think it's the molecules of the CD that causes the excitation.
So the molecule in the CD itself will cause the excitation that you will or will not observe. Is that right?
Yes,
Is that what you say on your conclusion? You said that
there is no excitation.
yeah, no excitation when you put the CD.
Yes.
I wanted to ask all of you the same question. The question states clearly that you have to use plastic material. Do you know why it was like a specifically asked you to do the plastic material? Transparent plastic. Do you know reason why? Maybe the reporter. Oh no, reviewer first.
Oh, me?
Yeah.
I think maybe is it because biofringence is the material that has the ดัชนีหักเห the same so that if we use another matter because the plastic is when we production of plastic is we use to melt the plastic and so
Okay. The opponent.
Because of from the manufacturing, when we eject the plastic to the model and form them, so the density of the molecule of the plastic is not the same.
So it has something to do with density.
Yes.
Okay, about reporter.
I say it's because about the stress analysis, because this phenomenon can reflect back to the stress in the material.
Where does the stress come from?
The stress comes from
The stress in the plastic.
the stress in the material. It
Yeah.
comes from the manufacturing process.
Okay.
And sometimes it could be increased because I've seen a video on YouTube when they put something like this and with a plastic and they apply stress in it by pulling it and the color changes. So that means that stress has an effect. The light can refer to the stress in the material too. This is called photoelasticity.
Okay, go to your first slide. The really first one. Yes, with your name on it. Oh, no. Second. All right. All right, let me ask the reviewer first. Look at the pictures. Is that the same as his result? That you give the compliment to his result that he showed the really nice picture. Is that the same phenomenon? Yes or no? Reviewer first.
For his experiment, okay, we just focus on this picture. This picture, I think they used the eyes to see, but in his experiment, he has the diagram and take a photo, so it's not the same.
It's the same.
So is this the same? Yes or no?
No.
The opponent.
I think no.
Okay. Want to explain a little bit because the reviewer have a chance to explain it. So
Because his result fringe in his results his fringe pattern, his result is not the same at this picture. So I think this picture is because of reflective polarization.
How about the reporter? Is that the same as what you reported?
I must say that I said before to the opponent that this phenomenon, there's two parts. There's the transmission part and the reflective part, which the reflective part I will be doing it in the future. But right now I'm just doing it in the transmission mode of the polarization.
This is not transmitted.
There is some sort of transmissions because when light hits the surface, some of it is refracted and some of it is reflected. And the light we see this, I think, is from both. But what matters more in this is the reflective angle. That some colors that have different wavelengths we cannot see because it is completely absorbed. So there's only one color that can appear. Not one color that appears, but a combination of colors that appears that we can see in this picture.
Okay, maybe reporter. So in your case, let's say that I have light. I'd go to some material, let's say the CD case. When the polarization change, do you expect the color to be different? Let's say that, maybe, sorry, I did not think it through. Let's put the white light pass to a CD and the polarization change. Should you see a different color? Let's say, let me be more specific. Let the polarization change from the linear polarized to circular polarization. Just that. Will you expect the color to be changed that you can see?
I guess it will change.
Can you explain why?
Why? Because white light is composed from many colors. And when we see it individually.
Yeah, let's
So
say that every color change from the linear polarized to circular polarized.
Every color changes.
From the
Linear
you have
polarized.
white light, you have our source color that you said. All change from linear to circular. You will expect to see any.
From my point of
colors.
view, I think that is impossible.
No, just make it up. I just make it up.
If make it up, I think it will change, but the pattern will be the same, but the colors will differ.
Same for the opponent and reviewer.
Sorry, but I can't remember.
You'll always be. Okay. One more time, both of you, okay? Don't ask me again. You start from the white light, pass to a piece of plastic case.
Yes.
All the color change from linear to circular polarization. Do you expect the color to change? I mean, first you see white. After you pass this through, you expect to see the color to be different?
Do you mean what color that I expect to see?
So you have a white light.
Yes.
First there is nothing, you see white light.
Yes.
Now you have a piece of plastic. And I say that the polarization change from all linear to circular polarization. Do you expect to see different color?
Yes, I do.
Okay, so reviewer.
Yes.